Hi everyone, we are back, and this time, as we discussed last time, we plan to discuss all the versions of YOLO, and we have again Vardhan Dongre with us, masters
Hello.
in. Yep, thanks Vardhan for this. So, would you like us to give us like a quick overview? What are we planning to do today?
Yeah, sure. So we have YOLO, and last time we did just a review of the YOLO paper, like going through it. But this time, like we know that there are like multiple versions of this paper, like from V1, V2, V3 till V5, and we plan to do something like a comparison between the all the versions. So we will move from version 1 to V5, and we would so V1, as we have like discussed in detail. So just now we will just give some a brief idea and the introduction to the what we saw in V1 and what the limitations were. But then we will transition from V1 to V2 and simultaneously like from V2 to V3 and V3 to V4 in that manner.
Awesome. Yeah, like the main goal is that we identify the limitations with each paper and how the next version added some component to overcome that problem. So it's that's why comparison of each version will help us to identify how to solve those problems. All right, so without much ado, we can start the version 1.
Okay. So yeah. So we know YOLO, it's like a one stage detection model as compared to the two-stage detectors. This is like supposed to be the fastest of all the object detection algorithms at the time it came out. So the idea was that you have an input image that is divided into a grid of some S by S grid, and each grid has some specific number of bounding boxes. So here they kept it to like 7 by 7 grids, and for each grid there is two bounding boxes in them. And so the idea is that the the algorithm tries to identify if there is an object present in a grid cell or not, and then tries to fit that bounding box with and tries to find that IOU as compared to the ground truth bounding box. So there's this whole equation that was discussed last time, and we went in detail about it. I think it's in upper portion, like on page 2 or in the last page, yeah. Even in the previous one.
Oh, the IO
Uh,
equation.
yeah, so yeah, this one. So basically, this is like the confidence prediction equation, which is like being used here to calculate the scores. And and yeah, I mean, like there were some issues regarding the resolution that they were using. So initially, the resolution was kept to be like two in 224 something. Like, can you just make sure like it's 224 by 224?
Yep. It was 224 by 224 for image uh, classification, and then they moved to 448 by
Right,
448 for
right, right,
object
right.
detection.
Yeah, so let's talk about like what the problems were. Like last time we briefly discussed the limitations of this first version. So main first thing that even in the paper has this section on limitations also. So we can just refer to that for this. So one thing is that there is that the bounding boxes are imposing some strong spatial constraints on each grid cell. And by that you mean it means that each grid cell is supposed to have only one object, but when it happens to be like in a grid cell there are multiple objects, the algorithm is not able to identify that if there are any more than one object present. I think it's in section 2.4, so you can just scroll to there.
2.4. Got
Yeah,
it.
this is. So yeah, we were talking about like what if there are like multiple objects clustered together, and what will be the detection in that case. So the bounding box will just be over one object, and if there are like multiple small objects flock together like the flock of birds, then this is where this algorithm fails. The second is like, uh, there is this case of handling uh, the sizes, like it's working on some coarse features right now, and the idea is that if we can work on some finer features or not. And then the third one is that which was called as the localization error, that there were so as they put it, like the small error in large boxes is generally considered okay, but if there is a small error in a smaller box, then it's not, it shouldn't be considered okay, but it is. So there is no way of like mitigating it in this paper. So so basically, like if you want to summarize it, like what's the main problems that they identified were, uh, it's the localization first, and and the second is trying to identify like the smaller objects in the in the image. So you can just like, so do you have any like opinions on this?
No, no, like you correctly highlighted all the uh, challenges we have. So just to summarize the points Vardhan made. So one grid can detect one object at a time. So at max, this model can detect 49 objects. So the reason why it fails in smaller objects is if in a grid there are 2 to 3 objects, it will be able to identify only one. So hence, for rest of the objects in that grid, this model fails to detect that. Moreover, like just to compare uh, s- uh, about generalization. So compared to two-stage model, this model performs well to to identify objects in new domain or scene, because in two-stage it localizes and just do object detection in that small domain or small region, rather than region of interest, rather than the whole picture. So those kind of models are not good compared to YOLO, which is better to identify objects in new domain.
Yeah, and I think I will also point out to the fact that, so like precision and recall are like very important factors in classification, and the model right now, like the version 1 had like very poor recall, and that is also where the next versions like focus trying to improve that uh, factor in. So yeah, so that is what I would like to also point out here.
Yeah, and just so that we haven't discussed precision and recall before. So my understanding is, let's say in an image there are a lot of motorbike cycle. If you increase the precision, then it will be able to also sometimes tag cycle as motorcycle, because you lose uh, the generalized object detection. Like I was saying another example in another domain where one should have a right balance of precision and recall, because too much low precision will sometimes fail to identify that particular object, and too much large precision can also identify another object which looks similar.
um so do you mean to like compare precision like an accuracy? Are you, is that what you're suggesting? So because like there is this discussion that if your model is too accurate on your data set, then it's probably not able to generalize. And are you like trying to say that if the model has higher precision, or and that is also a cause for that? Is that what you're
uh,
suggesting?
I think that might be kind of overfitting problem. I was pointing out, I saw an Apple developer presentation where there were like 3 bikes and 2 cycles in a scene. So if when they had like high low precision, it was even tagging the bikes as motorcycle. But when they had high precision, so instead of 3 bikes, it was able to detect 2 bikes. So it's a balance of precision and recall, where if you make it very low, you might miss out some object. If you make it very high, you might lose all the objects in that particular category.
I see. I see. Yeah, that might be a case too. I think I haven't seen that though, so maybe that can be also something we can consider. But yeah, so the point was like recall was an issue with because like subsequently in the next paper we will see that they mention the first version had like low recall, and that is and localization error. So these two are like the summary points that we can like take from here, like from the first version, although it is fast and it's pretty decent in its predictions and detection and classification, but then it suffers from localization issues and a poor recall. And that's where the version 2, if we can go on to that now, uh, is going to focus.
Yeah. I was thinking, can we do like a quick 1 minute run through the model architecture, because it would be interesting to compare like different model architecture across those models. So if
Yeah,
I'm
sure.
yeah, so if I get it right, it takes image from 448 by 448, and for the first, I think, 24 layers, it's taking from ImageNet. And basically YOLO is a regression problem to predict the bounding box. So once they do classification on using convolutional network on the 24th layer, they flatten it. And as you can see here in the 4096, the last 2 layers are fully connected uh, layer, and then they do like prediction for each of the grid cell, which class it belongs to, what's the confidence score for the bounding box, and then it will be able to predict in this 7 by 7 cross 30 tensor.
Yeah, that's right. So basically the architecture is somewhat based on GoogleNet, and they have like removed their that inception layers from here from it. So so mainly like as you said, there are like 24 convolutional layers and then followed by 2 fully connected layers. And this is like, so basically they haven't like uh, done, apart from like taking out the inception layers, this is very similar to the GoogleNet. If
Got it. Yeah, so we had those 3 challenges, our limitations of that paper, and now we will go deeper into YOLO V2. Uh,
okay,
yeah.
yeah, so basically Yolo V2, now we have a new version. And as you go through their abstract, they say that um, it's so there are like different terms here, like at, so they say at 67 fps YOLO V2 gets like 76.8 map on VOC 2007. At 40 fps V2 gets 78.6 map, outperforming state of the art methods like faster RCNN with ResNet and SSD. So just to like break it down for anyone who is not so familiar with these terms, is like, so you have these videos that are running at 67 frames per second, and on those videos the V2 has this mean average precision, that is map of 76.8. So by mean average, so you have this precision per class, and if you take a mean of all across all the classes of the precision, that's you get the mean average precision. So basically they are saying like at different rates of videos, one is at a 67 frame per second, which is like a very faster as compared to 40 frames per second. There is an accuracy of 6 7, not accuracy, but the metric is like map here. So they get 76.8 map, and for 40 fps map is 78.6, which is like At that time, it was like state of the art compared to even faster RCNN, which is like a two-state network.
I see. So yeah, I think the paper says better, faster, and stronger. So as you can see, uh, from 45 to 67 frames per second with good accuracy, it's a big jump.
Right. So basically, there one more thing that is very interesting in this paper is that they come up with version 2 and then they transform it into YOLO 9000. That is what something we can also discuss later as we progress. But yeah, I mean, I would be happy to hear your thoughts also, like if you have any inputs to give on V2.
Yeah, like I was thinking that I had like one point for why it was faster, why it was stronger. If you can maybe elaborate on that. So one thing to clarify between V2 and 9000 is in V1 it was able to predict like 20 class of object, and initially they proposed this modifications on V2 and they were able to do those 20 class, but then they increased the number of objects to 9000, and that's why they named that model as 9000.
Yeah. So one thing that is interesting, what they have done is a joint training algorithm, and they actually like pointed out that if you see in the introduction, it says that so there are like two tasks here. Like one is you need to identify if there is an object or not, and then the next task is you have to identify what object it is. So first one is like detection, and then it is classification. So you have this data sets based on detection, and then there are data sets that are specifically curated for classification. And the point here is the detection data sets are not so great and are very limited as compared to classification data sets. So that is why if you are training a network based on detection data sets, then there is some kind of like you are limited in terms of resources because there are not enough objects in the data, or there is like if you go on annotating it, so it's an expensive and very tedious process and don't want to get into that. So what to do in that case? So that is what they came up with a joint learning algorithm where they expand their data set by joining both the detection and classification data sets. That's an interesting idea. And that is where in the next like paragraphs you will see they pointed out that yeah, so they say that we propose a new method to harness the large amount of classification data and expand the scope of current data detection systems.
And so for joint training, uh, for V1, they used like Google Net pre-trained model for uh, training, and they did like some 20 epoch or something. I don't remember for the object detection. So when they say joint training, is it like training from scratch or?
No, I think so for this model for V2, they used the darknet 19 as the backbone, which was pre-trained on ImageNet. So first they do it for classification and then they go for detection. So the darknet 19 is like it's an implementation in C and CUDA. So you can look it up on like the website of the author. So the main thing here is they first do a classific training based on classification and then they go for detection. That's what I understood from the paper. And so my idea is that they pre-trained it on ImageNet and then they fine-tuned it on like the higher resolution images so because the point here is they wanted to train on not the coarse level features as what they did in V1. So they initially trained it on the ImageNet 1000, which had like this 224 by 224 size, but then they fine-tuned the network on the desired size, that the resolution that they want. So I think that's something around 416 or 448. So that's what 416 or 448. So I'm not so sure
Yeah.
about it, but then that's the high resolution that they are looking for.
Yeah, it says like 416 input images instead of 448 by 448. So I think like just to clarify, when we say coarse features and fine features, it reflects to the stage at which we do classification. So if the smaller size image tends to have more finer feature, right? Or
So what you can say here is that if you have this higher resolution, so you have this fine grained details in the image, right?
yep.
And those fine grained details can be extracted in features. So now the feature becomes like very finely detailed feature set. But if you reduce the resolution of the image and then you are taking out the features out of it, so they are like coarse features. That is what I think in terms of the interpretation here. And so the idea is that if you have this coarse grained features, then they are not so like effective in like for the for the for the algorithm to do what it's supposed to do. And if you have a more finer feature set, then it's much more effective.
Yeah, I think you're totally right, because I just recall an regressor model of MNIST data set, and like if you have like in the bottleneck, the image gets very blurry, so you can't detect the finer features. So I think you're right. So I think they were proposing some RPN or something to avoid localization error. Like I think the search. Uh,
So yeah, actually we actually jumped on towards like the network, but
yeah.
let's clarify like what happened. What's the big differences between
Okay.
V1 and V2? So the main deal that like summarize it in three main points. One is like uh, using batch normalization after each convolutional layer, and they attribute like some 2% improvement in the MAP for by using batch normalization. The second is the high resolution that we were discussing right now. Like they are using finer detailed, uh, fine features as compared to coarse ones. So that refinement or like using higher resolution for classification is as another factor that is like improving the MAP. And you can see it says like its increase is almost of 4%. And the third is like use of anchor boxes. So that's another reason for like why the this V2 is like performing well as compared to. So basically anchor boxes is like try to solve the localization problem that we were facing, and we can go in other details also later, like if we when we proceed in this paper.
Yeah, like there are like good images as we proceed. Yeah. So as you correctly pointed out, batch normalization, high resolution, and convolutional with anchor box. Is there anything else? I just recalled. So the point which I was making about like transfer learning and retraining, it was like for 10 epoch for ImageNet. So yeah, cool. Yeah, so more than 1,000 images. So more than 1,000 objects. So it's pretty impressive. Oh, anything about dimensional clusters?
Sure. So basically what happens with anchor boxes is that you need priors, and priors are like you need some initial dimensions where to begin from for the anchor boxes. And let's say for each grid cell you decide to have like k anchor boxes, and each anchor box has like this different size aspect ratio. So one question for you is like, what sizes should I choose? Can I just choose those sizes randomly? Like, how should I define those anchor boxes? Like, what aspect ratios? If I'm having, let's say, I have 5 anchor boxes for each grid cell, So what aspect ratio for each anchor box should I take? What the dimension should be? So this is where what they do is dimension clustering, and what they suggest is that they perform a k-means clustering on the data sets to cluster the anchor box dimensions in those ground truths to identify like what priors should they begin from. So that's what I'm thinking what they have done is. And the idea is that they kept that number of clusters to 5, what they found as like a good optimal number of clusters that can find the best number of anchor boxes that are present in the data set. And so I think this is for VOC. And so what they suggest is that most of the anchor boxes were thin and long, not very squarish as compared to rectangular. And this is what the dimensional cluster idea is, that they just try to find what the best priors are.
I see. And I was reading about k-means clustering. So if I get it right, so let's say if there are like 100 points in your uh, domain, and you have k equal to 5, so the algorithm will uh, do some processing and will divide the whole domain into like 5 partitions, and the k the one partition's mean value would be k1, k2, k3, k4, k5. So what I'm guessing is in your in your data set there would be like a lot of objects with different aspect ratio. So to determine like what aspect ratio would be good for the whole data set, maybe they are pointing out all the aspect ratios, then clustering of those, and then those means are the aspect ratio you will do for training.
Yeah, sure. Those are the 5 means that they found out, like the 5 clusters centers that you can say, and that's what they use as priors.
Awesome. We discussed IOU last time, so
Yeah, yeah. So I is like very commonly used for like the bounding box criteria. Like you have a ground truth bounding box, and one is a predicted, and you just need to see how much overlap is happening there.
mhm. Direct location prediction. You can like stop me if there's any point in this which you want to highlight.
Sure.
I think like
So let's. Okay, yeah. Go
go
ahead.
ahead. No, it's fine. I was just gonna point out like the way they were uh, computing. So they were normalizing to the whole grid from 0 to 1, and then for that aspect ratio, uh, they were predicting like these values.
Can you like say that again? Like I
Yeah. I'm not sure it was like true for YOLO V1 or V2, but I recall. So instead of predicting the exact like width height of the anchor box, they normalize the whole grid cell into 0 to 1, and then they predicted value relatively based on that.
yeah, that's right.
Yeah.
So I mean, let's go on like YOLO 9000 now, because it's later up in later parts of the paper, and that's something also interesting we can.
I see. All right. And just I might have forgotten. So the reason it was faster, is it because the network was had lesser parameters? What caused it to be faster?
Uh, s-
Oh,
so we initially said that like in the very beginning there are like three main reasons for this. One is use of batch normalization after each convolution layer. So that has helped in improving the MAP. The second one was the use of higher resolution images for classification, and the third one is use of anchor boxes. So anchor boxes like trying to solve that localization problem.
Yeah, like I thought those three factors were contributing more to the accuracy of the model, but like, what's why is it faster than YOLO V1? Is it because the number of parameters in the model are lesser, or maybe uh, there was some point which I have missed out.
Can you point it out in the paper, like where you
Like,
about this?
I just want like a very simplified version, like why it's faster. Like, is it because of because like in YOLO V1 you had the original model, and then they had like a shorter model for mobile deployment, so you get more compute speed but also you lose accuracy. So the way I believed was, if you want a faster model, sometimes you just reduce uh, the depth of the whole model architecture so you can predict faster. So what caused that increment in the speed?
So if I'm if I understood it correctly, like their idea was more on like addressing the limitations from V1 and not like achieving like much more faster inference rate as compared to V1. So the problems for V1 were, like we said, localization, lower recall, and inability. Well, it has like this only 49 grid cells, so it couldn't like go beyond that. So that was also an issue, and that was the like these are the main differences from V1 to V2. And I don't think there is like an enough comparison you can make in terms of like the fastness of V2 as compared to V1,
I see.
because they try to address the issues, these issues that I mentioned, rather
Correct.
than making it much faster as compared to V1.
I see. And I think just looking at this, they have like 19 convolutional layers and max 5 pooling
Hmm.
in this model, compared to here where they have 24
24,
convolutional.
yeah.
So maybe that might be one of the reason it's faster, because it's less deep. But the reason, like, I was not sure because that was taking 45 frames for detection and this was 60. So all right, I think so that caused uh, the model to be faster. For stronger, I think this is an interesting concept of word tree, where like they had
Yeah,
like a node based search.
yeah, so it's actually like trying to like learn the linguistic deep ideas of like of the objects also simultaneously here. That's what their like explanation there is. And like about the, I mean, we can go in details like if you want, like, but about the word tree, but I think this will be like a very long discussion if we
Yeah, yeah,
discuss word tree.
yeah. I think yeah, we can move on. The last thing I want to add, because in one of the examples, I think the way I think they were proposing uh, this to be stronger was, let's say in YOLO V1, if there is less confidence score or less score on the classification, it would give some, like, if it's a lower than threshold value, it would give some unknown class or something. Here, if let's say it's not able to identify Airbus, then it will go to the upper node of airplane and give that as classification. So it's stronger in that sense, that even if your score is less on classification, it will go back to the node which is higher and give that as classification.
Yeah, I mean the idea is like you if you have this tree structure where you're identifying like of the finer nodes or the leaf level nodes, and if you are not able to identify those, then you go back one node up in the structure and label it like that.
Correct. All right.
For the
You
9000 though, let's just briefly discuss that before moving on to V3. So 9000 is basically just that you are expanding from 20 classes to much larger number of categories, 9000 object categories now. And this is what they say as like joint optimization or joint training between classification and detection. So basically what is happening is they have like mixed these detection and classification datas together, and then they have used it to train the V2 and next like convert it into YOLO 9000.
Yeah, yeah. Initially, like when I was reading it, at some point I got confused. Wait, is it YOLO V2 or YOLO 9000? But it's like very small difference between those two models. So yeah. Is there anything else you want to add on YOLO 9000, or should we move on to V3?
I think we can move on to V3 because like you 9000 is just like you are expanding the object categories there. And the interesting idea is like the joint training. And if like people who are like interested in, I would definitely suggest like to try to focus on how they did that joint training there.
All right. So wait,
V3.
I'm just wondering, like, what were the limitations in V2? They didn't share that in the paper, right?
Not really. They didn't discuss. There was no limitation section in the paper.
Yeah.
What we can just say here is that uh, if you just like go to the one graph in the paper where they have like accuracies compared. This is the inference graph, not this one.
Yeah.
I think it's higher up. This is V3, right? I'm saying
Yeah. Yeah.
V2.
Oh, you.
Uh, Up in the where there are like accuracy comparisons in a graph. A
Oh,
graph.
this. Hmm.
Yeah, this one, figure
Oh,
four.
figure
Figure
4.
four. Yeah, yeah, yeah. Yeah, so you see here that where YOLO is like as compared to other networks. So YOLO is the sole YOLO is around like between 60 and 70 at something around like 48, 47 frames per second. YOLO V2 is like all the blue dots that you see. And as you see that the frames are increasing, the accuracy is decreasing.
Yeah, and it's important that like initially like YOLO uh it was capitalizing on the fast inference time and prediction, but it was compromising on accuracy. Now this one is beating two stage on accuracy as well as time. So it's
Yeah.
quite s- groundbreaking.
Yeah, so you see this YOLO is here right now. YOLO V2 is around here at the same, somewhere around the same frames, FPS, if you can say. But then as your FPS frames are like increasing, it's like the MAP is going down for YOLO V2, and that's something we can probably look into V3. Probably let's see if that they improved it or not.
Sure. Uh, do they have like similar? This is inference time.
So basically, if I make a distinction between V2 and V3, it's the backbone. So the for V2 it was darknet 19. Now they have like a different darknet 53 here as a backbone. and that's the only major difference that I can point out between the two. And the effect is better accuracy.
Yeah. And like it's so much interesting that in V2 there was 19 convolutional layer, and it was like 5 times better in terms of accuracy. And V3 has 53 layers. So I bet they are scoring a lot higher in terms of accuracy. Oh yeah, they have compared. So 19 is 74 and V3. So is it faster than V2? But I remember. Uh, so I was reading an article and they said clearly that V2 is faster than V3, and you can see it's 78 FPS versus 171. But accuracy is a bit higher than V2. 74 to 77, not bad.
So if you want to like compare the inference time, there is a graph. But let's talk about this table first. So
Yeah,
one thing here is that there are two factors here: top one and top five. So for people who are not like sure what top one, top five is, top one is like you have this object, you identified it, and you the model classified it as, let's say, class one, and the actual ground truth was also class one. So if they are like matching, that's then you get a score, right? That's the correct score. So the point is, what if the first so the basically what happens is your model is creating this probability distribution across all the classes, and so the highest probability associated with the class is actually assigned to the object. And if that is the first choice which has the highest probability, is if it matches the ground truth, then it's correct. So instead of going for the first one, you can also ask like, what are the top five uh, classes that the model has predicted for this particular object, and if among those top five your ground truth lies, then also you get a score. So these are like two metrics, top one and top five here.
I see. And just to give an example, if let's say there are 100 objects which it can predict, then maybe first object got like 70% score, second object got 30% or 20%, and relatively scores are assigned. So top 5 is like what was the highest score of the top 5 objects which the model predicted. And I guess sometimes top 5 would be important, because if let's say there is very less difference between first and second, like 30, 40, it is probable that sometimes the second object can be the actual class.
Uh, yeah, I mean, yeah, the second the so this is like this multinomial distribution that you get, and out of like the first five classes, maybe one of those first five classes is actually the ground truth. And that's why you see like top five is like a higher as compared to top one. So the idea here is that the model is able to at least among the top five classes, there is a ground truth the model is able to identify.
I see. How should we proceed on this? Should we like talk about the key changes, or should we go section by section?
um so we can go to the like this first figure, like on the inference time first, just to show what's happening, what's the difference. So if you see V3 compared to the other detection networks, so you see that it's pretty fast in terms of inference. And so this is the pink one is the Yolo V3, and the time is like pretty less, uh, but the MAPs are like okay as compared to the other. networks. But yeah, the main idea is like it has to be fast. That's it. Uh,
I see. And so I think at one point I got confused. So it's important that inference time is when it sees an image, how much time it took to predict the right classification and object detection. And there were earlier when it was saying like it was able to process 60 frames per second. So it's just like one divided by the inference time. This is in milliseconds, so it's zero point zero 0.02 per frame. So it, I think it's able to predict 50 images per second if you just divide one divided by 0.02.
yeah. And another is like I think so we discussed that the difference between V2 and V3 is the basically the backbone. Now you have this larger network with 53 convolutional layers, and this has actually like made it much better in identifying small images. That's what they suggest. And other than that, it's like so there is this one issue of like the IOU threshold that I saw some articles mentioning, as well as like the paper also. So the paper doesn't explicitly talks about it, but then there is this idea like if the threshold is like adjusted, then there are some issues with the MAP. So if you increase the threshold, then the MAP suffers.
Correct. And one thing I think once you make the network deeper, all the convolutional layers like in the whole network, it will be able to abstract features at different scale depending on how you resize it. So I think that is important, that how maybe, yeah, so the problem of identifying small objects can be resolved by making the whole network deeper.
Yeah. S- Yeah, I mean that's a pretty common notion you of deep learning. Like you make all these networks deeper, but then there are some other issues that you start facing as you go deep. But yeah, no, let's we are here to discuss more on YOLO rather than the deep the issues faced by deep networks.
So
And
wait,
we can keep another whole video on that also.
like just a thought. So this was able to do like 50 frames per second, and it has 53 layers. And Yolo V1 was doing like 45 frames per second, and it had like 24 layers. Hmm. Wonder why that is faster, even if the network is deeper.
So you mean like for V3?
Yeah, so V3 has 53 convolutional layer and it was doing 50 frames per second prediction. And V1 has 24 convolutional layer and it was doing 45 frames per second. So logically, like 53 should take like at least lesser than 24.
I would disagree here because, like, I mean, of course, the results show that it's not the case. But then I think one thing you can attribute here is also to the residual blocks here. So you have these residual blocks, as you see, and these are like skip connections. That's also one important uh, feature that you can say as a distinction, which distinguishes this network. And other than that, I don't know. I can't like put a finger on like why would you say that one has a higher frame rate and like capacity to analyze higher frame rates as compared to other.
Like my assumption can be wrong, but it's just like I thought the parameters here are more compared to YOLO V1. So the more parameters we have, the more computation it might take to do that. So that's why like it might affect the inference time.
If going by what they have like discussed in the paper, the idea here is more on like improving accuracy,
Yeah, yeah.
and that's what I would say, that their objective was to have a more accurate model here rather than more sped up or speeding up the previous versions. But and that's what they have achieved also, right? So the accuracies have like improved as compared to the previous version. But I don't know if what we can specifically say about the speed.
Yeah, like, it was just a thought. I think we have crossed like 40 minutes, so we can like speed it up. I see this is predicting at three different scales. So, and four bounding offset, one for object prediction, and 80 class predictions.
Yeah, it's pretty much similar to the formula we discussed in our previous video, right? That s times some that formula that was in the output tensor of the model that it was for V1. It's very similar to that. And if someone wants to make sure what it means, they can look at the previous video.
Yeah, yeah. I I might be wrong, but when they say at three different scale, for some reason I thought so when the convolutional goes from like it's doing prediction at not at the end but like some intermediate prediction at after 10 layers, after 20 layers, and after like 40 layers. So at three different scales, is it like the size of?
No, I don't think that's what they are saying is the system extracts features from different scales. So when you are saying extracting features, you are not in the inference stage right now. It's the fact that you have different scales of the inputs, and from those different scales, you are taking out the features. So if you go on the table one, yeah, on on the right side, yeah, the table one, yeah, this one. So it's not like you are making predictions at any intermediate stage here. It's not like that. The prediction is after the softmax, which is like going to give out the probability distribution. So the idea here is the residual blocks are like providing inputs from the previous layers as it is. And that's why that is one reason you can say like different scales you have different scales here.
I
But
see.
I'm not sure why they say three.
Yeah, like i I saw like they're mentioning like feature pyramid network because yeah, I was imagining similarly where like in your convolutional when you have image like from 448 to smaller resolution, they extract features at this intermediate layers like that, and they take from all these three layers and do prediction at the end. So it's like feature extraction at different resolution of images.
That's true. That's true. That's pretty accurate. So basically, you have this different sizes of the inputs, and that from those different sizes, you are extracting the features. That's what happening is. That is what you can say.
Yeah, so it's the scale they are referring is the size of the image while in the deep network.
Yeah, I would say input though, not the image.
Oh yes, sorry, input. Thanks for correcting. All right, moving on. Things we tried that didn't work. Anything you found interesting in that section?
Uh, so I think one interesting thing was the offset prediction, what they have tried to do here, and uh, that's something I was also wondering why it didn't work. And they say that we found this formulation decreased the model stability and didn't work very well. Other than that, I'm not so like pretty much they have like explained it why the other two didn't work. But for the first one, it's just like it says model stability was an issue. So yeah, I'm not so sure why that happened.
And apart from that,
So
we can.
maybe you can like jump on to V4 now. Uh, After like this paper is the paper after which the original author like stopped working on the updates, and we there is like no proper paper out after this. So we I think for V4 you can find a paper, but there is no documented paper for V5, not even on archive or anywhere else.
I see. So, like, what were some like key changes in V4?
For the V4, the like in terms of performance, I can say like it's performing better as from V3. It's like more, its MAP has increased for higher frame rates. Uh, if I could like just say what's like the major improvement, what we can say is the way the detector works has is now different in this. So you can yeah, you can go into the paper if you want. Yeah, if you see like the first figure here, just to like quickly see what the differences are from V3. So you see that for similar frame rates, like it's like having a higher average precision, and even like it's like faster than efficient at, which was also a very interesting paper. If you ever want to like go through it, it's an interesting idea in efficient at.
Yeah, is that by Google? Like, so there were two networks which, like, Google and Facebook combined every model into one whole framework where you can access like one stage, two stage, everything within that. So yeah, yeah, there was like efficient that and some electron that or electron net. One was by Google, another was by
Yeah,
Facebook.
so efficient at is definitely by Google, and I'm not sure which other one you're referring to, but yeah, efficient at is from Google's team, and it's a very interesting idea. Like I would suggest, like for anyone who is interested in uh, to go through what they have done. It's is like there is this FPN idea of FPN by FPN, which is very interesting, and the graphs that they generate and how they generate that graph is also very an interesting idea.
Yes. And like I think the major change, if I remember it right, it's like they're introducing bag of freebies and bag of specials.
Right. So this BOF and BOS is the main like the difference in the way the network is operating and performing detection. So I think they say that it affects the training time and the inference time, but then it is improving their accuracies, and that's what they like the objective was to improve, to make it more accurate.
Is to increase variability of input images so that the design object model has higher robustness.
Yeah, so I would like say it like an augmentation kind of technique. So you have this data augmentation techniques where you like change the brightness, do perform random cropping, flipping, vertical flips, horizontal flips. You so you perform these in order to like include more variability in your data set, and that's something on those lines that they are doing.
So yeah, so instead of like augmentation, they're using freebies. So it's just extra data.
You can say that, yeah.
Yeah.
They're like adjusting the data set. You
Yeah.
uh,
Random scaling, cropping, flipping, rotating. Yep. Pixel wise adjustment. All right. In bag of specials. Oh, they're introducing attention mechanism, which is whole another topic.
yeah. So these are the BOF and BOS. That's what I can say. Like is the distinction in terms of V3 and V4, and that is helping it like achieve higher accuracy.
Got it. And lastly, I'm just checking if they have any limitation first. Okay. And we don't have YOLO V5 paper, right?
No, so far it's only like in you can use it, but there is nothing to discuss what's. Uh, I mean, they are going to come with a paper so very soon. So let's see. But all I can say is much faster, not faster, but much accurate as compared to V4.
Yeah. I was wondering, like in V4 till V3, or yeah, till V3 they were doing like MAP, and suddenly in V4 they were doing just AP.
So I think they addressed this idea from changing from MAP to AP in their V4 paper, and you can like maybe go on that section if you want. Uh, it's not a big deal, uh, what I can say. But yeah, I mean, this is sometimes even someone who is looking it from a, of an another perspective, like not who's not so familiar with it, it kind of it can be confusing. Like, why is this difference between the metrics?
I see. Okay, so let's conclude then. So overall, YOLO became popular because of its fast speed and compared to two-stage models, and they were planning to deploy this in edge computing or like your similarly Android or Raspberry Pi. So they want like lightweight models which can do good prediction. So YOLO proved that it was possible by converting the problem of separate classification and separate object detection into one problem where they were doing classification, like as you can see at 24th convolutional layer, and then regression, like they were predicting both at the end. So that was a achievement, and it was giving decent results. But after that, as we saw in V2, where YOLO had MAP lying in, I would say, between 60 to 64 range. So it was still lesser than other uh, two-stage model. So YOLO 2 V2 changed the whole game by having faster and more accurate than two-stage, which is like unbelievable. So it was quite efficient compared to uh, two-stage models. So, and then uh, even that, like I assume that in that V2, because it was uh, because of the network, it was still missing some finer features. So in V3, they made the model quite deep of 53 convolutional layer, and in that model, they were able to uh, detect finer features. And I think across the models, the the things that change apart from the model architecture was how they are doing prediction of those bounding boxes. So you can do like selective search, which is done in two stage. You can also do like anchor box, which they introduced in paper. So it's about at what stage do you do image classification, and how you approach the regression problem. Those are the two key to consider in while doing object detection. And in V3, wait, in V4 they had bag of freebies and bag of specials. So in V3, uh, they had deeper network. It proved uh, faster and efficient than other papers. So yeah, Vardhan,
And it had those residual connections, skip connections in it, in the
yeah,
network,
this residual connections. Yep.
right?
In V2, I think few things important were batch normalization. Instead of 224 by 224, they were doing classification at 448 by 448 and introduction of anchor boxes.
Yeah, those were the factors that like helped increase the MAP.
And in V3, was it in V3 or V4? They were doing yeah, prediction at three different scale. So it's a concept similar to feature pyramid. There, instead of doing image classification at the end, they do intermediate, take intermediate inputs and then extract those features and then do classification. So I think that's how they are using more finer features and doing better and more accurate prediction. Few of the limitations which V2 overcome was V1 had limitation of only one object per grid. V2 can do many objects and even like around 9,000 classes. So it's provided, it broadened up the prediction scale as well.
Yeah, and it has like those issues of not able to detect smaller objects in the image frame, and problems related to localization, and that's what the next versions tried to like improve upon. Like, so these were like the initial problems you faced in V1, and V2 kind of like just swept across all these problems, and then later on from V3 to V4 to V5, what you see is that you are only focusing on increasing the accuracy of the model, and maybe if speed, if that's possible.
Yeah, and I'm wondering, like, generally the footage we take is either 30 frames per second and 50 or 60 frames per second. So V2, V3 were already talking in 50 or 60 frames per second range. So I think at that point the fastness was not a problem. The accuracy was then the only challenge left to overcome. So from V3 to V5, we see models which were more accurate.
Yeah, and so I would also suggest like people to like look at the TED talk of the original author. It was I think in 2018 or something in Mumbai, uh, and it's an interesting talk. Like, although it's old, and the the field has like moved beyond like some of the ideas, but this is like an interesting talk. And if you are interested in this object detection algorithms and classification algorithms, then you should definitely take a look at it.
Awesome. So I think we summarized the topic. It's almost an 1 hour mark. And I hope you guys found it useful. If you want any other paper you want us to discuss, we are happy to do that. And but then what should be our next goal?
um, so we are on one stage detectors. We can definitely do two stage ones. There are like a series of improvements from the original two stage detector that came up, and then later on like moving to the state of the art which is right now. There are like other ideas of like machine vision and segmentation and detection, which is motion segmentation and motion classification, and that's also an interesting idea we can go into.
I see. Yeah, normally I don't say this, like please like, share and this video, but I think like Vardhan is quite busy and I really appreciate his time for this review. So if you like more such videos, please share this content.
Yeah, please do so.
All right.